So in the last couple of sessions, we were learning about basics of semiconductor physics, right? Uh, and in this session, we'll discuss about the transport processes, especially on semiconductors. So in semiconductor, we know, right, there are two types of carriers, electrons and holes, right? Now, when you make a device, when you try to use a semiconductor, the important phenomenon is the movement of carriers, right? The transport of carriers. So what are the different ways they basically move, or they basically transport the current within the semiconductor? So this is very important. So uh, to understand that, so we'll just define that what are the different phenomenon basically take part in the process of conduction or conduction of charge, right? So first thing we'll discuss about carrier drift. Some of the concept you might have already studied. So first we'll discuss about drift phenomenon, then there is another phenomenon, important phenomenon is called diffusion, right? Diffusion. And then we have carrier generation, right? I'll just simply write generation. And we have carrier recombination, right? Recombination. And then we have again different tunneling process will happen. So we'll discuss all this as we go on. So tunneling, like we have studied tunneling diode, right? So this tunneling effect is also take part in carrier transport. And then we have impact ionization, like avalanche photodiode, later on we'll learn. So it's called impact ionization. And one important thing I forgot, it's space charge. Space charge also has a lot of impact on this transport phenomenon. So space charge. And then we have thermoionic emission. Thermoionic emissions. So these are the 8 phenomenons, major 8 phenomenon. So first two, drift and diffusion, are the major, and then these two next, and then there are special phenomenon. These are fall under special phenomenon. So all these phenomenons basically impact the carrier transport or the conduction mechanism in a semiconductor, right? So at thermal equilibrium, if you see a semiconductor, let's just draw a schematic. Oops. Okay. So if you take a semiconductor material, I'm just doing a two-dimensional picture. So in this we have, at room temperature itself, we have seen there are electrons and holes, right? Even in intrinsic semiconductor, right? So we have both the carriers. Let's say it's a silicon, for example. Now at room temperature, within the semiconductor, these electrons and holes, they are moving randomly, right? Why they're moving? Because they have thermal energy, right? So because of the thermal energy, they are moving randomly within the material, right? So net current in this situation at thermal equilibrium, the net current will be 0, right? Net current is equal to 0 at thermal equilibrium. And we know from the energy theorem of equipartition that it tells that under thermal equilibrium, the average thermal energy of a free electron. So these electrons are in conduction band, right? Whatever the carriers we are talking about, we're talking only the electrons present in the conduction band or free electron, we can tell them. So under thermal equilibrium, the average thermal kinetic energy of this electron is equivalent to half kT per degrees of freedom, right? Oops, degrees of freedom. So this is, we are talking about, okay, let me just write down the theorem. It's called Theorem of Equipartition of Energy, right? Theorem of Equipartition of, I forgot to change this tab setting. Pressure I need to change. Of energy, the sensitivity basically. Okay. It's a theorem of equipartition of energy. Okay. So it's this is under thermal equilibrium, right? Now for an electron, if let's say it has a thermal velocity, so let's define few parameters to understand better. So this is VTH is the average thermal velocity of electron. Average thermal okay. Average thermal velocity of electron. Okay. So in this situation, what will be the kinetic energy? So electron is having velocity VTH. So the kinetic energy you can write the, I'll just write in short, kinetic problem. Okay, kinetic energy of, it's not writing. Okay, kinetic energy of electron is equal to, so we know that half mv square, right? So half mn vth square. What's happened? Board is inverted for me. For everyone, is it? The board is inverted now? Huh?
No, sir. No, sir.
Just see, Gauri's Shankar, maybe maybe you're using some mirroring software, something, mirroring add-ons or something. It should not be. Should okay, so kinetic energy of electron is half mn vth square. Now, what is mn? Fine. So mn is our effective mass of electron, right? No, effective mass of electron. Okay. So this is the kinetic energy of electron. Now, where does it coming from? This kinetic energy is coming from again the thermal energy, right? So this we can equate it like this half mn vth square is equal to 3 by 2 kT. So for each degrees of freedom, we have from equipartition energy, we know that half kT is for each electron, sorry, each degrees of freedom. Now in a three-dimensional space, the electron can move in all three directions. So it has basically 3 degrees of freedom. So total energy, we can write it with this equation, right? We can equate them basically. All right. Now, now if we look at the order of this, these parameters. Oops. like the order of VTH, or the average thermal velocity. So this, you should know a little bit of this order, right? Some idea. So it's about 10 to the power, again problem, 10 to the power 7 centimeter per second. Okay, so this is for silicon. And again, this thermal velocity changes with temperature, right? So silicon at room temperature, it's like around at 300 Kelvin. So it's 10 to the power 7 centimeter per second. It's quite fast, right? And yeah, it's the thermal velocity. And then we'll define two more parameters, mean free path and mean free. Okay, just let me describe this one by one. So one is our mean free path, and then we have mean free time, mean free path time. Uh, it's hanging. I need to restart, but let's complete the class if possible. Mean free path, so it is we defined as mu, or not mu, we generally define it as L for electron, Le, or for hole it is LH. And mean free path, similar mean free time is tau c for electron and tau c prime for holes. So what is mean free path? Mean free path is, so as I said, that at thermal equilibrium, these electrons, or the carriers basically, electrons and holes both, they are in random motion, right? Like they are moving randomly. This, right? So they are having collision with the lattice or the different ions or different atoms, right? So the mean free path is the distance a carrier travels between two successive collisions, right? So again, it's a average, mean is average. So average distance the electron travels between two successive collisions, right? And the time it takes is called mean free time, right? Okay. So mean free length, mean free length. Okay, VTH we defined, right? The order is about 10 to the power 7 centimeter per second. And the mean free path, it is of the order of 10 to the power minus 5 centimeter. So after each, 10 to the power 5 centimeter, which is 10 micrometer, right? So each 10 micrometer, you can expect a carrier, electrons and hole, they collide with the another charged particle, another atoms, or any lattice scattering happens. Okay. So you can easily find out the mean free time then. So mean free time will be again mean free path by velocity, right? So it will be 10 to the power minus 5 by 10 to the power minus 7 centimeter per second. So the unit will be second again. So it will be about 10 to the power 12, 10 to the minus 12 second, which is actually 1 picosecond, right? It's very short, right? Picosecond mean free path. So each picosecond there is a collision, you can imagine. Each carrier undergoes a collision. Now at thermal equilibrium, they have this random motion, and we can see that this is the collision rate, this much they can travel before hitting another collision, right? So in this situation, we don't have any effective current because it's a random motion. So equal number of electrons and holes, if you take a time average with a cross section, over a cross section, If you take a time average, it will be like 0. The net charge flow will be 0. So there is no current flow. Now what if we bias this semiconductor with an electric field, right? We can attach to electrode. So I'm just drawing again two-dimensional. Let me move it up. So okay. I don't know, it's not going to my hand. It's getting hanged. Okay. Hope okay. So this is the semiconductor. Now let's say if we bias this with a battery, right? So we're just connecting positive and negative. It's a piece of silicon, you can imagine. We put two electrodes on two sides and we just connected with a battery. So basically we are applying some electric field, right? So what is the electric field direction? Positive to negative, right? In this direction. So we're applying electric field in direction. Now the electrons present in this semiconductor, they will feel a force opposite to the electric field, and the holes, they will also experience a force towards the electric field, right? So the electron will start to move basically towards this positive side, or this on the left side electrode, this electrode, and the holes will move towards this electrode. Now you can see that there is a net current, right, in this system. So this movement is called drift velocity, or drift, or this movement is called drift. So basically the carriers are drifting, right? So how can you quantify them? If you want to quantify this drift, so it's very simple, right? So how much force an electron will experience under electric field E? So it is very easy, right? The force is nothing but charge. So for electron, we will consider charge as minus Q, and the electric field, right? Q into E. And this also defines that this negative sign, it tells about that the force it experiences is opposite to the electric field, right? This negative sign here, it tells about that. And now because of this force, the electron is moving, right? And so at what speed it will move? That's called drift velocity comes into picture, right? So the velocity it will move because of this electric field is called drift velocity. Okay, so it's Vd we write, or Vn. For electron we write as small vn, not capital V, we write small vn. Okay, so this is the drift velocity. And now in this, so we have basically drift velocity, and also the thermal velocity is also present, that Vth is also there. But this drift velocity, I mean, they are again vector, right? These velocities are vector. Thermal velocity is randomized, but drift velocity has a particular direction. So it has a net, you know, net movement of charge we will see at a particular direction, right? So how to equate this? So because of this drift, this force, there will be change in momentum, right? So what is the momentum of an electron having drift velocity Vn? So the momentum of the electron will be Mn, the the effective mass of the electron, into Vn. So this is the momentum of the electron, and it has to be, and this momentum is coming from again the applied electric field, right? So we can write it down as Q into E into tau C. So why this? how to understand this. So the left side we can see its momentum, and again we can write momentum on the right side. It is like momentum is force into time, right? Because these are collision, so impact kind of thing. So it's momentum is equal to force into time, right? Is this these are impact kind of thing, very quick collisions. So Q into E is the force, and the time is again the mean free time, right? So if you equate them, then you will get, from here you can calculate the drift velocity of electron. So it's a Vn equals to minus Q tau c. So I'll put all the constant here, Q by tau c by, we have Mn, it will come into the denominator, right? And then we have electric field, right? Okay, so within the bracket, all the parameters you can see they are constant for at a particular temperature, because this tau c will be temperature dependent. Other two Q and Mn, they are constant even with temperature, right? But for at thermal equilibrium at a particular temperature, the quantity within the bracket is always a constant term, right? So that term is we defined as the mobility of carrier, or in this case mobility of electron, right? So we write it as minus mu n into E, where mu n is Q tau c over mm, right? So it's called mobility. Electron, right? So if you look at carefully this mobility, this three quantity, Q as I told, it's constant, Mn is constant, and this tau c only will have impact on temperature, right? We'll see that how tau c varies with temperature. This is also another important, or this mean free time, right? But at a particular temperature, this is a constant factor. So this is the drift velocity of electron, and a similar way we can calculate for the holes, right? Of course, they move in opposite direction of electron, but if you do the same mathematics, you will get that Vp, or drift velocity of hole, right, it's small p, is equals to Q, and this tau c will be different for holes. So I'll just put tau c prime, and the effective mass of hole is mp, and electric field. Here you notice that I didn't put the negative sign, because the drift velocity of electron, drift velocity of hole, it will be in the same direction with the electric field, right? So this is for the holes. Now again here we can write mu p, right? Same way, I'm not writing. So this is the mobility of holes, right? Now when it comes to conduction phenomenon, the electrons and holes, they cannot simply freely move in the lattice, right? When they try to move, they will again see different scattering phenomenon. Why? Because in the material, so there are different potentials, because in the real semiconductor we will be doping with some impurity atoms, right? Let's say aluminum or phosphorus. So those atoms will be ionized, right, even at room temperature. So they will create a different potential well or different, you know, different this force environment, right? Because these electrons and holes, they are charged particles, so they will be affected by any surrounding charge present nearby, right? And also at room temperature, the atoms, they are not idle, right? They are vibrating, right? That is called the phonon, right? So each lattice point or each atoms, they are vibrating with their position, right? And because of this vibrations or the presence of lattice, these electrons and holes, they will get scattered, right? They cannot freely move. They cannot move in a straight line freely, right? Even the electric field is there, they cannot simply, electron cannot simply move straight line, right? Because the presence of different atoms, impurities, ions, right? So again, they will, their path will be deflected. So there are two phenomenon, major phenomenon we consider in this to understand this movement of charge. One is our lattice scattering. Lattice scattering of, very slow, lattice scattering. Okay, so in lattice scattering, as I mentioned, so this happens because of the presence of different atoms in the material, right? And those atoms, they are vibrating in their positions. So when the electron try to cross, they will be get deflected because of these vibrations, right? The potential energy, it's not fixed, so it's changing at room temperature because of their vibration. So due to this, the electron will scattered through, right? They cannot move in a straight line, they will be deflected. And so what it will impact is on the mobility, right? Because in the mobility, you see there is a okay, let me just pull it down. So in this mobility, you can see there is a factor tau c. Qmn fine constant, but this tau c will change, right? The collision will be more frequent, so tau c will lower, right? As the temperature increases, let me just take a condition that we are increasing the temperature, let's say. So if you increase the temperature, the lattice vibration or the atom vibration increases, right? So the probability of collision with the atoms, I mean this scattering phenomenon, will increase. So if the scattering phenomenon or the collision probability increases, then the value of tau c will decrease, right? Because they are colliding more frequent now. So tau c will decrease, and so the mu n, right? So mu n will also decrease, right? So as temperature increases, we can see the mobility of carriers, it decreases due to lattice scattering. Okay, and theoretically it is shown that this mu L, or the mobility due to this lattice scattering, so mobility due to the lattice scattering, this impact, it has an impact with temperature of T to the power minus 3 by 2. So you can see it's inversely, I mean, they're inversely related, not directly proportional. And it is theoretical, it is shown. Sorry, not equal, cannot write equal, right? So it's proportional. Okay, so they are proportional to this. Now let's try to understand another phenomenon called impurity scattering. So here we can see it's inversely, or if temperature increases, the mu L decreases.
Sairam, sir.
Sairam?
Sir, is the mobility of a carrier
Uh-huh.
related to the conductivity of a semiconductor, sir?
Yes. No. conductivity depends on mobility. Mobility is more, more fundamental.
Sir, but we have learned a property that
Uh-huh.
in semiconductors, as temperature increases, the conductivity increases, no, sir. So if conductivity increases, it means that the
Yes.
mobility also should increase, no, sir.
Yes, that's a very good point. So that's comes into our second scattering. You will get the answer here now. You are absolutely right. At room temperature, most of the semiconductor, as you increase temperature, mobility increases. But we'll see this because of the second factor we have. So we have another called impurity scattering. So let me just write it off, then we'll explain that. So it has two components. So one, lattice scattering decreases, but impurity scattering increases the mobility. Okay, so let me just write it off. Impurity scattering. Okay, so impurity scattering, again, we will define it as mu I. Okay, so in mu I, it is theoretically it is shown like this. So it is proportional to t to the power 3 by 2 by nt. So let me just explain the value. So what is nt? Nt is concentration of impurity or impurity concentration. Okay, so why in case of impurity this mobility increases with temperature? So let's try to understand this concept. So the impurity scattering comes because of the presence of different charge or different impurity atoms, right? So at room temperature, we know most of the impurity atoms, they will be ionized. So they are basically impurity ions in the lattice or in the crystal system, right? Now when an electrons and hole passes near to the impurity, they will get deflected, right? Because they are, let's say, positively charged. So electron will be repelled off, holes will be attracted off, but it will impact their movement. It will reduce, right? So that's why you can see that number of impurity, if it is more, then the mobility will reduce more. Don't compare directly with the conductivity, because conductivity has some few more parameters in it, like it depends on carrier concentration also, but we are now talking about only their mobility. Or so we have more number of, let's say, let's consider donor. So we're talking about n type material. So donors are basically positively charged, right? So you have more number of donor atoms. Now when an electron try to move, right, let's say one electron is moving, and then it will get attracted to this donor atom, right? So it will get deflected, but again the electric field is there, so it will still move this direction. It will bend towards this ion, and then again it will move, but what happens is it got delayed, right? So the effective velocity will reduce, or the mobility will reduce. And what about temperature now? So as we increase the temperature, what happens is these electrons or holes, they move faster. Their thermal velocity also increases, right? So the velocity of electrons and holes, it increases as we increase the temperature. And in that situation, what happens is these electrons and hole will stay very less time near to this charge, near to this charges, donors or acceptors, whatever. So they'll spend less time. So their impact will be lower, right? Because thermal velocity is more, so their movement is fast now. So they'll spend less time near to this positive or negative charge, donor acceptor ions. So this impurity scattering or the effect of these ions will be lower. So that's why as you increase the temperature, the mobility increases. The impurity scattering decreases. or the mobility due to impurity scattering, it will be more as we increase temperature. Is it clear, this concept? Conductivity part will come to that. But try to understand the speed. Yes.
For lattice scattering, also when temperature increases, the thermal energy of electron also increases.
Yes, but remember lattice scattering we discuss about the neutral atoms, neutral atoms, and the collision with the, 1 minute, collision with the neutral atoms. So, wait. Okay, so this atom, let's say, when the temperature was lower, the atom was vibrating maybe just this much, and as you increase the temperature, the atom, this vibration, this will increase. So effectively, when electron try to pass this atom, it will get more deflected, or the collision probability increases because this vibration amplitude has increased as we increase the temperature. Don't consider charge now. When we consider about the impurity scattering, that time only we talk about the charge concept. I mean deflection because of the charge. But here it's collision because of different atoms. Is it clear?
Yes, sir. Yes, sir.
Yeah. So these are two, contradictory, or one will try to increase, other will try to decrease with temperature. And this phenomenon, or if you draw these curves together, then you will get a complex, not complex, you will get a peak, right? Let me just draw a very rough schematic. Before that, let's equate this thing with with the mean free path. Okay, so or mean free time. So total mean free time, if it is let's say tau c, then 1 over tau c is equals to, because this mu L is directly related to tau c, right? Let me just pull it back once. Here. So Q and Mn constant. So tau c and tau c, or the mean free path, is directly related to this velocity, right? Mu n. Okay. And now we are trying to correlate this two. Okay. We're just combining these two because these two phenomenon, this impurity scattering and lattice scattering, they're happening simultaneously, right? So the 1 over tau c is equals to 1 over tau c lattice. So there are two phenomenon. One is lattice and another one is our impurity, right? And this inverse of them, they are additive, or the frequency, you can say, right? This is time. So 1 by time is the frequency, or it talks about how frequent they will collide, right? So they are additive in nature. And this 1 over tau c, we can write it as 1 over mu c, because the other two parameters, they are constant. So 1 over mu L plus 1 over mu I. So the total mobility of the system, or of the crystal structure, in a crystal structure, the total mobility of the carrier, this mu c, is related with this relation between these two phenomena, right? Okay. And if you plot this for a material, if you plot temperature versus mobility, it is mu c, the overall one, then you will see this kind of oops. You see this kind of nature, right? So we are plotting with temperature. So this side is increasing with temperature, right? So it is to the power 3 by 2, and this side is to the power minus 3 by 2. So what is happening is at higher temperature, the lattice scattering takes over. The effect of lattice scattering is more at higher temperature, and then at lower temperature the effect of impurity scattering is more. And for each semiconductor, each type of semiconductor, there is a optimum temperature where you can get maximum mobility. And this is very important because when you design a semiconductor, right, we always want the highest mobility, so which will impact the conductivity, right? So that's why for semiconductors, not always at room temperature it will be the best semiconductor, right? Sometimes at lower temperature it may work better, sometimes it is at higher temperature. So this can be, again, theoretically people can calculate and find out that what is the best suitable temperature for a particular semiconductor, and this is very important also, right? So for typical next class I'll bring some data, and I'll show you for a few known semiconductors that how this mobility changes with temperatures. Okay, but you got the idea today that uh, why this kind of peak we get, right? Because of these two phenomenon, one compete with each other, right? Impurity scattering and lattice scattering. So far, any doubts from this? Okay.